Hi all, so today I'm going to be doing the group work for November 10th. So this covers chapter 8, which is a lot of different reactions and reaction mechanisms. Okay, so first up is describe in your own words what Markovnikov's rule is. Hang on, this camera's... Okay, describe in your own words what Markovnikov's rule is, and I describe this as the electrophile is added to the less substituted side. And when we have carbocations, I think I spelled that wrong. And when we have carbocations, this makes a lot of sense because the carbocation wants to be on the more substituted side, and that's where the nucleophile will attack. But also we see this in formation of the mercurium ion or the bromonium ion. There's a partially positive on the more substituted side, and that's also where the nucleophile attacks. So the nucleophile attacks on more substituted side. So for explaining why it's favored by oxymercuration, demercuration, if I were to draw just a regular old alkene, and then the oxymercury, so it's HGOAC, the extra cloud of electrons that makes up the double bond here is going to attack the mercury, and then this bond breaks, and it doesn't form a carbocation. Instead, it forms this triangular shape, and I chalk that up to we don't know everything about how this reaction mechanism occurs, because we can't shrink ourselves down to the molecular level or anything. This is kind of confusing. This is a separate figure. But we know that rearrangement doesn't occur, and we know that then the nucleophile comes and attacks here. So there could be multiple ways this triangle is formed, this mercurium ion is formed, but this step, the mercury is more on the less substituted side. And what I think the reason for that is that there's already enough electron density to sort of support this, and there's some sterics around here, so it kind of pushes the mercury over to be more on this side. That's the best explanation I have. So there is a partial positive here, and that's where the nucleophile will attack. So you can explain that with pictures or with words. I'm fine with either. And then to explain why anti-Markovnikov is favored by hydroboration oxidation, that one is actually all about sterics, because really on this one, the boron has to line up with the alkene. And if the boron was on this side, see all these steric hindrance, that's not actually going to be favored. So instead, it lines up where the boron with its two H's is on the side with the hydrogen, so that there's less steric hindrance, and this hydrogen is on the side with the methyl group, so there's less interference here. And then the reaction proceeds, and the boron goes on the less substituted side, and then we end up with that eventually being alcohol. To draw the stepwise reaction mechanism of oxymercuration, demercuration, and on our last quiz, actually, a lot of people didn't get this exactly correct. So I really want you to focus on remembering that arrows go from the negative to the positive. And for these addition reactions, usually the alkene is negative because this double bond is essentially two extra electrons that are floating around between these two carbons. So it does have a strong amount of electron density. And so that will attack. And we talked about it like the negative people attack, positive people don't. So we're always going to go from the more electron dense area to the less electron dense area. So in this case, our mercury is going to act as the electrophile, or the thing seeking for electrons. This will come and attack, and then this bond will break. So I actually drew it up here, but that's step 1, alkene attacks and formation of the mercurium ion. So to get full credit on a quiz question, you need to draw these arrows. We look for each arrow to see that you understand that these electrons are coming to make a bond with this Hg and this mercury here, and these electrons are leaving and departing so that the mercury maintains the amount of electrons around it. So the mercurium ion looks like this. There's more of a partial positive on this side than the other side, and so actually that is going to be where the nucleophile attacks, and then you also have your OAC, and that's minus. So this is I'll redraw this, plus OAC minus. So then your water that's in solution will come and attack here, and this bond will break. And again, I guess I should have drawn this down here, so I'll redraw it down here. So the formation of the mercuranium ion is step 1. And then so that you can see step 2 distinctly, the water attacks, and then that forms the oxymercuration product. So the first step is oxymercuration, the second step is demercuration. So you have your OH2 plus, your methyl group that was already there, and then your mercury is on this side because this bond breaks. So the only attachment point is over here. Okay, and then water is deprotonated, and I don't care what you draw deprotonating the water here, either the water or the OAC minus, whatever it is that you want to, or you can just write base. Any of those things are acceptable. It'll deprotonate the water. Sometimes people will just draw minus H plus, like you lost an H plus. Any of those are acceptable. And then you have your HGOAC. So this is your oxymercuration product, and actually all of the products that go through the triangle formation originally add anti. So this would be a wedge, and this would be a dash, and you'd also get the enantiomer of this. That's the full product. However, in the next step, when the mercury is replaced with hydrogen, the stereochemistry is lost. Because of the reduction, that's the NABH4 trading out for the mercury. So you don't retain the stereochemistry. So your final product is actually a mixture. But in this case, that doesn't even matter because there's a plane of symmetry right through the middle. And if you had this plus the enantiomer, it would be a meso compound anyway. So the plane of symmetry means that it doesn't matter. How would this reaction be different if you had alcohol instead of water as a solvent? So, well, I do want to say, first of all, on this, you do need to make sure that you're drawing every arrow if you want to get complete credit so that you show us that you understand the flow of electrons, which is all about what these arrows are doing. And you do need to know the relationship between the two products. So if the question is draw the answer with the correct stereochemistry. So we did that up here, but then the stereochemistry is not retained on the final step. And then the regiochemistry is that it adds Markovnikov, and we did that. This attacked on the more substituted side. Does it make multiple products? Well, the final product, it does not retain stereochemistry, and it only makes one product because there's a plane of symmetry. So that answers all those questions. And then if this would be different if you had alcohol, so the only step that's different starts from B. So we have HGOAC, and then we had the methyl group over here. So let's just say we have ethanol instead. So this is what attacks, and this bond still breaks, so that step is the same. OCH3, and it still has its hydrogen, it's positive, and then you have your HGOAC, and these do add anti, so you would get this plus the enantiomer. You lose the proton in a deprotonation step, so you can just draw any old base coming here and taking the proton, and you end up with your ether instead of an alcohol, and then this gets replaced with hydrogen, and so your final product would look like this. Okay, so be sure when you're going over mechanisms that you really understand the flow of electrons. Now, the stepwise mechanism of HBr, this is really similar to acid catalyzed addition. So the first step is we're going to get a protonation. So this double bond that was here, the electrons are going to go attack right there at the proton. And then we also have Br minus, but when this double bond disappeared, when it moved in to form this bond right here, it left behind an absence of electron right there. So that's where the carbocation comes in. And the Br minus is going to attack, but whenever there's a carbocation, you always need to think of the rearrangement step. So here, let me actually draw these step by step so that you can see it better. So step 1, the alkene attacks the acid, and that forms a carbocation and a bromine nucleophile. Rearrangement may occur. So you can usually draw the rearrangement with the arrows shifting, the electron shifting over. So this hydrogen has moved over here, and now the positive charge is right there. And then I'm not going to draw that hydrogen anymore because it's implied. So we've added a hydrogen right here, and we had a rearrangement where it shifted over. So I'm not drawing either of those. Hydrogen added right there. And then the Br minus will attack, and you'll end up with your final product. Now, we have the correct regiochemistry. It adds Markov-Nikov, which means the carbocation is going to form on the more stable side. So that's really important. But we haven't talked about the stereochemistry. So we know that the hydrogen adds on this side and the carbocation forms on this side to stabilize it, and then the rearrangement occurs. But when the nucleophile attacks, an sp3 hybridized is a flat plane, right? Or an sp2 hybridized is a flat plane. It's trigonal planar, sp2 hybridized carbocations, just like in SN1 and E1 reactions. So the nucleophile can attack from this side or from this side. So you're actually going to get a racemic mixture. So you can draw one with the bromine as a wedge and one with the bromine as a dash. And there's not a plane of symmetry here, so there are two different molecules, and these are enantiomers. So it does make multiple products. Okay. Now the stepwise mechanism of the given reaction. Step 1, the alkene attacks. So again, you'll need to draw all the steps here to get full credit, and you need to make sure the arrows start at the more electron dense area, so at the alkene, and they end up at the more electron poor area. So the first step is this attacks, and the Br minus is formed, but also the brominium ion is formed. And I like to draw, so this just shows the formation of one bond, but actually, really, this electron pair comes back and is donated because you get a Br plus. And we don't 100% actually know how this mechanism transpires. So it is possible that for a brief moment, a carbocation may form right here on this side when it attaches, but it doesn't form long enough for there to be rearrangement. So if that was too confusing to you, that's fine. I totally understand. Don't think about that too much. Just think about the triangle forming. But this does show you how this bromine started out with 6 lone pairs around it. Now it has 2 or 3 lone pairs for 6 electrons. Now it has 2 lone pairs with 4 electrons. And so the formal charge, if bromine starts with 7, then you take away 4 for the lone pair and 2 for the bond, and that's why that bromine is positively charged. So we form the brominium ion and the Br minus. And the next step is alcohol attacks. Now, if this was in a neutral solvent like CCl4, that's not a protic solvent, then the Br minus that's floating around in solution would attack. But if you have alcohol as your solvent, alcohol is protic, it's protonating that bromine, it's like pushing it out of the way, it's surrounding the bromine so that the alcohol has a chance to attack. So you can think about that if one of your friends makes a distraction so that you can make an exit. I don't know. It's something like that. And remember, there is a partial positive on the more substituted side anytime these triangular ions form. So you know the alcohol is going to attack on that side. And hopefully this looks familiar to you and reminds you, and then this bond breaks. Hopefully this looks familiar to you and reminds you of the oxymercuration product. So we have the CH3 and we have OCH2CH3, and that has a proton on it from where it attacked, and it does attack from the electrons on the oxygen. So the bond is to the oxygen here. And then on this side, we have the bromine because this bond broke, but the bromine is still attached on the other side. And as I mentioned before, these are usually, if you have the triangle, they're anti. So one of these will be a wedge and one of these will be a dash, but let's first deprotonate this alcohol. So you lose your H+, either do another alcohol or something in solution, and you'll end up with OCH2, CH3, CH3, and bromine. But these have added anti to one another. So let's make the OCH2, CH3, sorry, that looks kind of a weird drawing, as a wedge and the bromine a dash, but you'll also get the enantiomer, OCH2, CH3, with the methyl group being a wedge. This methyl group should be a dash. And the bromine. So you get this plus the enantiomer. So that should answer the product with the correct stereochemistry. We know the stereochemistry is right because they add anti to each other. So here one's a wedge, here's one's a dash. Here the other one's a dash and the other one's a wedge. Both products are formed because it can attack from either side. So either of those is viable. So the relationship is enantiomers. And they form anti to one another. So you get both of these enantiomers. Now, how the product would be different if you used ethanol for the solvent and water instead of ethanol is actually on this attacking step. You'd have water attacking instead. So the water would be the one that attacks, and this bond would break. And you'd get OH2 plus and Br. And then that would deprotonate, and you'd have your OH and your bromine. And see how the OH and the bromine, one's a wedge, one's a dash. And then if you had, and you'd also get the enantiomer. And then if you have bromine plus and CCl4, the Br minus won't be as impeded, so that actually will have a chance to attack and break this, and you'll end up getting two bromines added anti to each other. So bromine and your bromine, and then your CH3 is also still there, plus the enantiomer. So you should be able to hopefully kind of tie all these reactions together. Br2 in CCl4, Br2 in alcohol, Br2 in water, and oxymercuration, demercuration. Those all occur very similarly. They all have an anti-addition. With the oxymercuration, demercuration, we did talk about how it's anti initially, but then when you trade out for the mercury, it kind of makes things more confusing. But these are all very similar reactions. Okay, now we get into just, do you know what these different reagents do? And actually, osmium oxide, we talked about that you don't need to know the mechanism for this, but it adds two alcohols across the bond and breaks it. So the product here is OH. And if you want to know why it does that, we did put that online for you on the PowerPoint, but you just don't have to memorize how to do it on your own. Now, this alkene with HBr, this is an alkyne, but we already did an alkene with HBr, so it's going to go the same way. And I do have to draw out the mechanism because otherwise I get confused. So the carbocation is going to the more substituted side so it can be more stable, and the hydrogen will go to the outside, and then this Br minus comes here. So, and this bond was formed between the alkyne and the hydrogen by one of these bonds breaking and forming a bond instead between the alkyne and the hydrogen, creating this bond right here. So one of these bonds became this bond. And now the bromine comes in and attacks, and the extra electrons the bromine has around it, there's 4 around it here, it will make up that bromine. And now there's only 3 lone pairs around it, right? So one of those lone pairs made this bond. And these, hopefully you remember, the carbocation is sp2 hybridized, so it can attack from either place. So you would get a racemic mixture of this, but actually it doesn't end up matter because you don't end up having a stereocenter, because the reaction is just going to take place again, where you'll have the carbocation on this side, and now you've added, there's already a hydrogen right here. So you added 1, and now you've added a third, and you still have your bromine here, and then the Br minus that was formed is going to come and attack again. So you've added 2 bromines here, and then 2 hydrogens for a total of 3 on the other side. And just to make sure I didn't lose my carbons, because I always wonder, 1, 2, 3, 4, 5. Yeah, there we go. KMNO4 cold actually does the same thing as osmium oxide. It actually adds 2 alcohols. And in class, we talked about how scientists kind of have to decide, would they rather use osmium oxide or, sorry, I drew that wrong. Would they rather use osmium oxide or would they rather use KMNO4? KMNO4 doesn't yield 100% this result, whereas osmium oxide has a much higher percentage yield. It's much more toxic. So you kind of have to consider that. Also, we didn't draw stereochemistry on this. Sorry, we should have. And these actually add syn to each other. And these also add syn to each other initially, but this one, they're free to rotate on a single bond like this. So, and neither of them is a chiral center, so it doesn't matter. Right here, this one would be a chiral center. So that is important to note. And then O3 will cleave a double bond. You don't need to know the mechanism for this, although you can look it up. It's in the notes. And right in that double bond, it adds an oxygen on each side. So you retain everything. You just break it apart and add an oxygen on each side. So you started with this, and you end up with the ketone in the formaldehyde. KMNO4 hot does basically the same thing, except it's a more intense oxidizing agent. So it won't be happy just oxidizing here. It's actually going to go one step further, and it's going to it makes something that looks like this. And then actually this lone pair comes in and kicks that out. And I think that's the mechanism. Something similar to that happens anyway, and you end up with CO2. So KMNO4 is a lot more intense, and we'll learn the mechanism for KMNO4 later when you're in the chapter about oxidation reactions. Okay, BH3THF, this adds anti-Markovnikov, right? We did the thing where it was like, oh, the BH2 is too hindered, so it adds on this side, BHH, and then over here is H, and actually this is the double bond attacks here, and then this bond breaks and forms, and the transition state is this box. I did a terrible job of explaining that, but if you want a more thorough explanation of that reaction mechanism, please, please, please go check out my other video. And so these add syn to each other, so I'm going to make them both wedges, and that CH3 can be a dash. And in the first step, you get hydrogen on one side and BH2 on the other. And then it will get replaced with hydrogen on this side and OH in the second step. So the first step adds the BH2, and then the H2O2 NaOH replaces it, but it does have a retention of stereochemistry, so they still add syn. But I want you to know this hydrogen is implied. So a lot of times people will actually draw this like this wedge and this dash, and students will get the answer wrong because they know that BH3THF adds syn, so they're both supposed to be wedges, but that's the methyl group that was already there. That's the wedge, that's the dash. That implied hydrogen is a wedge right here, right? But it's not drawn, it's implied, and so people will actually get that question wrong. But this is formed, and so is the enantiomer. And then for oxymercuration, demercuration, the mercuranium ion forms. I'm not going to draw out the whole mechanism here, but the mercuranium ion does form, and then this water is going to attack on the more substituted side because that partial positive is there. And you end up with HgOAc on the less substituted side and OH2 plus. That gets deprotonated, and it's OH with HgOAc, and then that gets treated with NaBH4, and you end up with, oh, here, let me redraw that, this product. So if you know that mechanism and you know that it adds Markovnikov with no rearrangement, you can just go ahead and draw the OH here and the hydrogen here, and you'll know that. But I like to draw the mechanism out every single time. That's just easier for me. When I see acid catalyzed hydration, I actually just replace this with HA or H+. because the first step is that, or you can even do H and then HSO4. The first step is the alkene attacks that because it has extra electrons and that bond breaks. And you end up with the carbocation right here because the hydrogen adds on this side and breaks that double bond, right? It took these 2 electrons and made this new bond. And then that carbocation actually will go rearrangement because, boom, that's going to be more stable. So, and this should look familiar to you. This is a very similar practice problem to the HBr question we did because they go by the same mechanism. And this hydrogen's still there. It's implied, so I'm not going to draw it anymore. And then in the next step, your water will come in, OH2 plus, or OH2 will come in and take your carbocation, and you'll end up with OH2 plus, and then that gets deprotonated either by the water in solution or the HSO4 minus or whatever. It doesn't matter. And so you can just draw a base coming and taking a proton and the bond breaking, and you'll get an OH forms right there. I'm running out of space. Okay, so I'll just solve this one down here. So this is oxymercuration, demercuration, but with HGOAC. So this alkene will come and attack. And again, the mechanism is not required here on these practice problems, but you do need to know. Oh, I didn't do stereochemistry for these. So let me go ahead and do stereochemistry for the HGOAC and water. This adds the OH and the hydrogen add syn to each other, but actually it doesn't matter right here. So the OH and that hydrogen add anti to each other initially, and then you get a mixture. So you'd get a mixture of products on that one. And on this one, because it's a carbocation, this would also attack from either side, but there's not a chiral center there. So the stereochemistry doesn't matter there. But you don't have to draw the mechanism on all of these, but I like drawing the mechanism because it actually helps me see the flow of electrons and helps me know what that stereochemistry is going to be. It actually helps me. So this is the first step, and then the CH3, CH3OH is going to come and attack on the more substituted side, and this bond will break. And then we have OH, CH3, and then that will get deprotonated. And so you'll end up with a hydrogen up here that you can draw in, but it is implied. There's 3 hydrogens there. And then the OCH3. Oh, wait, this first, I said it gets deprotonated, and then also you go through the NABH4 to end up with your final product replacing the mercury. And initially, these two will add anti to each other, but actually because this is not a chiral center, there's a plane of symmetry right through the middle of this, it does not matter what the stereochemistry is. Your final product has this plus the enantiomer, but the enantiomer is the same because there's a plane of symmetry right down the middle. And I do want to draw your attention, though, that basically the difference between these two, they both add alcohol, or they both add a hydrogen in the nucleophile, and they both add them Markovnikov with no rearrangement, but with there's water, it adds OH and H, and if there's CH3, it adds OR and H. So you just need to notice the difference between those. And then this last one, this is the carbene mechanism. So essentially it acts as a carbene, which is a neutral carbon that will attack, and this will attack, and it forms a cyclopropane, and stereochemistry is retained, so these will still be trans, so this could be a wedge and this a dash. Or vice versa, you'd get this plus the enantiomer. Okay, the next question, question 6, is what reagents would you use to accomplish the following transformations? So this is kind of like the first step in a retrosynthesis problem. So I'm looking at this and I'm seeing the alkene, and if this alkene adds an alcohol to it, and it adds Markovnikov. So that means it could either be acid catalyzed addition of water across a double bond, or it could be oxymercuration demercuration. But if I drew this first one and it got protonated, there would be a rearrangement because this could undergo a methyl shift. And it doesn't look like rearrangement occurred, so I know that this is oxymercuration demercuration. It's kind of getting a long video, so I'm not going to draw out all the reagents, but you should know it's the HGOAC, THF, H2O, and NABH4. And then here, this adds water across a double bond again, but it actually happens anti-Markovnikov. So that makes me know it has to be hydroboration oxidation. I'm just going to write hydroboration oxidation, and so that's BH3, THF, H2O2, and NaOH as the reagents. And I do post the key online, so you can just look at my key online. And then this one is not addition of water across a double bond. It looks to me like this bond was cleaved and oxygen was added to either side of it, because now there's an oxygen where there used to just be a double bond, so it becomes a ketone. And I noticed that there's a hydrogen here and there's a hydrogen here, and it didn't get further oxidized. And on this side, these two hydrogens stayed intact. So you can have used hot KMNO4 to cleave it. So it has to be O3. Okay, ozone, and usually it's like either dimethyl sulfide or it'll be CH3. Let's see. I think it's SCH3 too, or something like that. I don't know. Something along those lines. And then sometimes it'll be like Me2S also. And then this last one, it looks like water is added, but not across the double bond. Water is added here and here. And that makes me think of the methyl shift that we saw taking place in the first question. So that's how I know it's going to be H plus and H2O for this one, because there has to have been a methyl shift to occur for this to work. So hopefully that's helpful for you. So the very last thing we're going to do today is this multi-step synthesis. So it says predict the structures for A, B, C, and D, and consider stereochemistry, all that stuff. So we know NaNH2 with NH3 actually abstracts this NH2 minus. This is just an acid-base reaction. And I would encourage you, when you have a multi-step reaction like this, I run through the questions with myself. Is this acid-base? Because that's what we learned first, and those reactions actually happen fast. So is there an acid-base reaction? If not, is it a substitution or elimination reaction? Or is it something we learned from chapter 8, right? So this is NaNH2 minus. So this is an acid-base reaction. We also learned this in chapter 7, I think, to create a carbanion. And so this would be the structure for A. And then this is actually reacted forward with this right here to do the next reaction, get B. And this is not an acid-base reaction because these all have pKs of like 50, so that's not going to go. So the next question is it substitution elimination? Well, this looks like a really good candidate for an SN1 or SN2 reaction to me, because there's a strong nucleophile and a primary leaving group. So I'm going to go with that. And if we react those two together, we would get, let's see, 1, 2, 3, 1, 2, 1, 2, 3. Okay, so now we have an alkyne that's substituted on each side. And then we have a dissolving metal reduction, which we know eliminates one of these carbon-carbon triple bonds, and it creates a trans double bond. And we know that because Lindlar's catalyst or the other ones always add cis, but dissolving metal reduction is the only one that adds trans. So our hydrogens are opposite each other, and our methyl substitutions are as well. And then the very last reaction, so this is actually, I should write, this is structure B, and this right here is structure C. And then C undergoes Br2 with CCl4, and that makes the brominium ion. So you don't have to draw the mechanism to get full credit, but you usually get at least some credit if we know that you understand it to some degree. Oh, this goes away and you have your BR. Sorry, that is a mistake of mine. Your BR plus. Sometimes I'll draw this coming back and attacking again. And your stereochemistry on these is retained when this is formed. So I like to draw this in the plane of the page, and this as a wedge and this as a dash. And then your other bromine that you formed right here, this Br minus, will come in and attack. And these are actually substituted the same way, so it doesn't matter which side it attacks. And you get a let's see, we'll have this bromine pointing down and then this bromine pointing up and this wedge and this dash. So that's your final product, and I suspect there would be an enantiomer, except that this should be a meso compound because there's a plane of symmetry. I haven't worked it all out, but that's very likely. Okay, and this very last one is a retrosynthesis problem. This is kind of like a challenge problem. It's a bonus. I wouldn't worry about it a ton for the exam or the quiz, but this is linalool, and it's found in lavender and other natural plant extracts, and it's often used for skincare and other commercial products. So when I'm looking from here to here, I see three main transformations. This has an alcohol where it doesn't here. This has an alkene where it didn't before, and this has an alkene where it didn't before. So it looks like we need to do two eliminations and an addition. If we do the eliminations first and make double bonds though, then when we add the water, that would cause a problem because then we'd add water in some other places. So I'm going to add my alcohol first, and I'm going to do that with oxymercuration, demercuration. And I would get an anti-addition or a Markovnikov addition of OH. I'm not going to do stereochemistry because there's not stereochemistry here, so I'm not going to complicate it further. Oh, I drew this all wrong. Br here, and now we've added OH here, and the hydrogen here, but that's implied, and the bromine. And now I want to do an elimination reaction. If I did a narrow site-Ceph product for both of these, you'd form a double bond here and here. But we don't want a double bond here, we want one here. So actually first I'm going to use a big bulky base, and I'm going to use a 1-to-1 equivalent of this. So like 1 mole of this for every 1 mole of this, so that this reaction is favored. And that would give me only one reaction taking place, only the one I want. This would only take one of these hydrogens, and then this leaving group would leave. So you'd end up with this. And then I do a narrow E2 reaction where I can have a hydrogen get stolen from here. The lone pair leaves, this goes here, and you get the site-Ceph product. Don't worry if this totally left you in the dust. This is more like if you're like, I don't know what she was saying and she went so fast. This is more just to challenge yourself and to really see if you have a good understanding, like beyond of the past few products or the past few chapters and retrosynthesis. So really focus on the other stuff before question 8 for this quiz coming up. But I hope that was helpful to you. Please reach out if you have any questions for me.